Hi everyone, today I would like to talk about clustering. This is the fifth video in the video series about the numerical linear algebra and optimization. Clustering is a very well-known and widely used technique in machine learning. It's a class of unsupervised learning algorithm. What does it mean? What do I mean by unsupervised learning? This means that you have no label or no ground truth for your data, right? So you are only given a data. And the goal is to partition data to k groups or cluster them to k groups in such a way that the data in each cluster are similar to each other. Okay, great. So that's the point of clustering and what is actually clustering in really high level. Now, what is the problem formulation? We are given n data points or n vectors if you want, x1, x2 all the way to xn. And as I said, there are n dimensional vectors, right? So the goal is that the objective is that to partition this data to k clusters or k groups according to some metric. Now, what is this k? This k, as I wrote here, k is a number of clusters, and n, capital N, is a number of data points or number of the vectors. And what do I mean by n dimensional? Each of these x, like x1, for example, is going to be n dimensional. x11, x12, all the way to x1n, right? Each of these vectors, right? They are n dimensional. Now, what do I mean by this symbol here? It means that k is much smaller than n, right? This is a reasonable assumption in real world, and it's always the case. N is the number of data points. Sometimes it's 10,000, 100,000. What is the k? Typically, it's 3, 4, 5. 20, 30, 40, 50, right? So this is the formulation for the cluster. Okay, now in order to better understand the clustering, we are going to discuss about some terminologies, right? The first terminology that I'm going to discuss is group representative. Now, for each cluster or group, we associate a group representative. For example, here I will call them Z1, Z2 to Zk. Why k of them? Because we have k clusters, right? Each cluster has one group representative. Z1, let's say, is a representative for cluster 1, Z2 is a representative for cluster 2, and Zk is a representative for cluster k. Good. Now, the group representative is chosen in such a way that minimizes this quantity, right? What is this quantity? It's defined as a distance between the vector xi, right, and the group representative corresponding to the vector xi. That's what this ZCI is. The notation might be confusing, so let me explain. ZCI, first of all, Z is a group representative, right? CI is defined as a group where the vector xi is assigned to, right? So let's say the vector xi is part of cluster 1, right? So then CI would be 1, right? CI is equal to group where the vector xi is associated to. If the data point xi was in cluster 3, then CI would be 3. Okay, good. So in a sense, this ZCI is defined as representative for a group I or for a xi vector. This is better to write for xi vector. Okay, let me just bring this one. Okay, so Zi is a representative for xi vector. Now, so we would like to minimize this distance. That's intuitive, right? Let's take a look at this diagram that I have here in the left-hand side. Yeah, I have 3 clusters and I have a bunch of points. Each of these points, let me erase this one and explain from scratch, right? So each of these points, let me draw them from scratch. So each of these points, we have, let's say, 3 clusters, right? This is 3 clusters. Now, in each cluster, we have some data points. Each of these data points, they are one of these xi's. For example, this is x1, this is x2, one of our data points or vectors. X3, X4, you have here X20, let's say X25, and then here we have X100, X105, and so on, so on and so forth. Okay, now we're going to go ahead and choose a group representative for each cluster, right? So what is this group representative? It can be one of the data points, right? It can be the average of data points per cluster. It can be anything we want. For now, let's assume it's anything we like, right? It doesn't have to be one of the data points. So let's say that this is a group representative for cluster 2. I call it Z2. This is group representative for cluster 3. I call it Z3. And this is a group representative for cluster 1. So it's intuitive that in the goal of clustering, we want to cluster our data points in such a way that the distance between the points in each cluster to the group representative be minimized. Meaning that, for example, if you consider cluster 1 here, this is cluster 1, you would like the distance, and remember in the previous videos, we defined the distance of between point A and B as a norm of A minus B. So we would like the distance between X1 and Z1 be plus the distance between X2 and Z2 or Z1, sorry, plus all level distance, let's say X6 and Z1 to be minimized, right? In that sense, we say that all these points are actually in this cluster, right? All these points are similar in such a way that they have a minimum distance to the group representative in cluster 1. Why did I use X6? Is because this is X5, this is X6, this is X7. Let's use X7, right? Okay, great. Now that we know what we are trying to do, let's have a better objective for our clustering. As I just explained, the goal in the clustering algorithm in general is to minimize this J class. This is our objective. So in order to define any algorithm, you should have an objective, because eventually you're going to maximize or minimize this objective, right? You can have multiple objectives for the clustering, but this one is the easiest and is the most common or the most widely used one. So let me tell you what this objective is telling us. Each xi is a data point, right? zci is a group representative. And what is this objective? It's defined as a mean square distance of the data points from the group representative, right? Let's call this one equation 1. So equation 1 is a mean distance of each data point x1, x2, xn from the group representative. Why do I say mean? Remember, we talked about in the previous videos, we talked about the average in the context of a vector. So for example, if vector x is defined as x1, x2, all the way to xn, let's use capital N for example here, then the average of x is equal to sum of all the elements of x divided by capital N, right? So here is 1 over n. The n in the denominator of equation 1 represents the mean, right, or the expected value. Okay, why is this a good clustering objective? Because this is exactly what I explained before, that what we are trying to do, we are trying to minimize this J class eventually. What does it mean? It means that we are trying to minimize the distance from the point x1 to the group representative corresponding to the point x1 plus minimize them plus the distance from x2 to the group representative corresponding to the point x2 and all the way distance from the point xn to the group representative corresponding to the point xn. We add them up and then we try to minimize this one. Okay, great. So as you see here, this J class depends on two parameters. depends on the cluster assignment, which is the CI. What does cluster assignment mean? It means that each data point is in actually is in which cluster, right? So let's say, for example, what is that one? Let's say this x100, right? The vector x 100, right? This is in cluster 3. This is cluster assignment, right? This is important. First, we need to identify this. If x100 is in cluster 2, then the objective function and everything is going to change, right? So the cluster assignment is that it's telling you that the point is in actual which cluster. This is very important in cluster. Actually, this is the goal of the cluster, right? This means that determining what is CI. And also choice of group representative, which means the ZJ, right? Remember I talked about the group representative. So for example, the group representative for cluster 1 is this Z1, right? We need to have a good group representative. There are, for now, we can think of it this Z1 to be as one of the data points or average of data points. And then we'll see how we can actually choose the group representative optimally, right? So remember two things. This J class depends on the group assignment and cluster assignment and the group representative. Now, what value of this J class is good? The lower the better. We are trying to minimize this. What is the best value? What's the dream value that we can have? 0. Under what case you get 0? J class equal to 0, right? We are adding bunch of positive numbers. It's equal to, they are 0. The sum is 0 when each of them is equal to 0. This means that x1 is equal to zc1, x2 is equal to zc2, and all the way to xn is equal to zcn. Okay, when we have this condition, in a real world, this condition almost never satisfies, right? But what does this condition say? This condition say that x1, data point 1, should be equal to the group representative corresponding to the data point 1. x2 should be exactly equal to the group representative corresponding to the x2. And xn should be exactly equal to the group representative corresponding to xn. What does it mean? It means that we should have n, capital N, group representative, which means that we should have capital N clusters. Therefore, each data point will be in its own cluster, right? This means each data point will be in its own cluster. This is extremely inefficient. You have 10,000 data points, you want 10,000 clusters. Of course, the error would be 0. Each point is in its own cluster, right? So this is never happens because we set the number of cluster beforehand in most of the clustering algorithm. And the objective that we have in our hand is to set the number of cluster to be much, much smaller than n. This is what I explained in the beginning of this video, right? So we don't get, so j equal to 0 never happens, right? So now that's why we try to minimize this j. The lower, the better for us. Okay, good. So we talk about that we have two parameters, the cluster assignment. For example, data point x1, is it in cluster 1? Is it in 2? Is it in 3? Which one it is? This is a cluster assignment. And the group representative, right, for each cluster. So it turns out it's really hard if you want to jointly minimize these two together, if they are varying at the same time. But what if we actually follow this strategy? What if we fix one of them at each iteration and then change the other one, right? And then keep doing this, fixing one of them, change the other one, and then fix the other one and change the first one. Okay, so for now, we're gonna fix the group representative and try to minimize the J class, the objective function for clustering, with respect to the group assignment. So meaning that we are trying to fix the ZJs, the group representative is the same. At some point in each per cluster, right? And we try to actually optimize the objective function for the group assignment. Okay, let's see. So here I explained that if we fix the group representative, then the best strategy to minimize J-class is to assign each data point xi to be the nearest point or to the closest point to the group representative. Why is that correct? Why is it very easy to see? Look at this objective function. I would like to minimize this objective function with respect to CI, cluster assignment, right? Let's take a look at this one. Do I have it here as well or not? I have it here as well. I can look at this one. So this respect to CI. CI is somewhere here, right? Xi minus ZCI square, right? So I'm going to minimize it respect to CI. I have CI in this for this set. But where else I have CI, right? I have n terms. This is the first term, the second, and all the way to n terms. I have CI only in one of them. The other n minus 1 terms do not have any CI. So if I want to optimize with respect to CI, all I need to care is this term. As easy as it is. We need to minimize this term. We need to minimize the norm of xi minus zci. Okay? Therefore, the minimum only happens if the xi has the minimum distance to zci. I'm going to go ahead and associate each data point to its nearest group representative. Okay, so let's write down this one. So fixing the group representative and optimizing for CI is equal to assigning each data point xi to the nearest group representative. Okay, so we solved one of the problem. What do I mean by that? Let's just make it clear here. I'm gonna first define some points here. The way I do that, we have like 3 clusters, right? Okay, so I'm gonna choose one group representative here, another group representative here, another group representative here. So let me just draw my clustering. And then ask myself if this clustering is good or not, right? So I fixed the group representative, these red dots, they are the group representative. Now I'm asking myself, what is the correct assignment? What's a good assignment? I take this point, this one, I call it x1. I ask myself, which distance is minimum? Yeah, this distance, I call it d1. This distance, I call it d2, or this distance should be straight line. I call it d3. Which one? By inspection, I can see d1 is smaller. So I say go ahead and assign the point x1. Let's call this one cluster 1. This is cluster 2. And this is cluster 3. I'm going to go ahead and assign the point x1 to cluster 2. So point x1 is a cluster 2. Okay, so this is an example of cluster assignment. Then I pick another point here. I pick this point. This is x5. I do the same thing. I go ahead and calculate this quantity. From here to here, I will call it d1. From here to here, I will call it d2. And from here to here, I will call it d3. I ask the same question. Which distance is the lowest? I realize that d1 is the lowest. So I tell myself that this point x5 would be assigned to the cluster 1. So x1 would be in cluster 1. So this is very easy. That's what happens when you just fix the group representative. You see, these red dots, the positions are not changing. Where you fix the group representative, and then you ask yourself, what is the correct cluster assignment? Okay, good. Now that we answered this one, and we realize that it's very easy, now we ask ourselves, what if I fix the group assignment? I said at this point x1, hey, I know the clusters. The point x1 is in group 1. The point x2 is in group 1. The point x3 also is in group 1. But how can I minimize this objective function, this J class, with respect to group representative? What is a good representative? What's a good group representative here, right? I know the data points that correspond to cluster 1, but what is a good group representative for cluster 1? This is what I'm trying to solve. Well, it turns out this one also is very easy, right? So remember the J class that we have. You can write it like this. Where K is the number of clusters and the number of group representative you have. This is very important. I'm going to draw another diagram here. So in this time, I'm going to choose K to be 4. So J here is 4. And each JJ here for this equation 2, and this is 3, each JJ is actually equal to the mean, remember, 1 over n of this quantity, xi minus zj square, the distance between xi and the group representative zj square, right? So this time, for what points? For points I, set of indices I such that it's in group J. Think of it like that. The indices I that are in group J, right? Group means cluster. So for example of this helps. This is x1, 2, 3, 4, 5, 6, 7, 8. So for let's say that this is cluster 1, 2, 3, and 4, right? And this is weird. So I'm gonna make that 1, 3, and this is 4. Okay. So here, for example, let's say we have 3, 4, 5, 6, 7, 8, 9. So let's say we have 8 points. Let's say. So and the points are this. The indices are 1, 2, 3, all the way to 8, right? And they're in cluster 4. So this is going to be G4. The set of indices that are in cluster 4. Okay. So I am looking at all the points that are in cluster 4. And what is the group representative, for example? We are trying to minimize over the group representative. We are trying to optimize. We don't know where that is. But in order to visualize that, let's say this is, for example, Zj here. So what does this objective function, equation 1 and 2 say? Equation 2 and 3, sorry. What do they say? It says that, equation 3 says that choose each cluster. We know the correct cluster assignment, right? For example, cluster 4. My goal is to find the distance between each data point to each group representative. So for example, the distance between this and the group representative, distance between this point and the group representative, distance between this point and the group representative, right? And add them up. This is for cluster 4, right? This is what this indices says, I in G, J, right? So for example, G4, cluster 4, the set of indices. For all these indices, for x1, x2, x3, all the way to x8, do the same thing, right? Calculate this distance. Okay, great. And then go ahead, do this one for J1, do this one for J2, right? And then, so each J is for each group. So for example, if you do it for this, J4 is for group 4, it's gonna be this G4, and then the distance between these points, xi minus z4, right? The group represented corresponding to the cluster 4. So you do it for J4, you do it for J1, you do it for J2, you do it for J3, and you do it for J4, and add them all together, right? That's going to be our J class. It's very intuitive, right? All it says is that calculate distance from the points to the group representative for each cluster, and then add them all. Very, very intuitive. We will do the same thing as well. It's not a new objective for our clustering algorithm. It's the same thing. We just write it differently. Okay, good. Here I explain how, what do I mean by that? So I give actually more explanation for that, right? I say, for example, assume the first 20 data points is gonna be in one cluster. So there's a more extended explanation, which is actually pretty much what I explained now. So I said that we are trying to minimize the score of distance of the points from the group representative. That's what this pink line says. So this is the group representative. We are trying to find each of these distances and then add them all together. So for the group J, then change the group, do the same thing, keep changing the group, do the same thing until you're done, and then add them up these points together. Okay, great. Then we are trying to minimize these quantities over Zj. Okay, so we are trying to minimize this J class for Zj. Okay, great. But now, wait a minute here. We just saw that, let me write one step here. We just saw that J class is equal to J1 plus J2 plus Jj, let's say all the way to Jk. Okay, good. When you are trying to minimize this one over, Zj, let me go ahead and put this one here. When you're trying to minimize this one over Zj, it means very interesting scenario. This is very interesting because Zj only appears in the Jj, right? What's the definition of Jj? We have it here. What's the definition of Jj? We have it here. This is what we want to do. If you calculate a Jk or a J1 and J2, we don't have Zj. We have Z1, we have Z2. If you are trying to minimize that respect to Zj, you have only one term out of K term that depends on Zj. The rest of them do not depend on Zj. So if you want to minimize the J class respect to Zj, you only need to minimize Jj respect to Zj, right? Good. Okay, so that's what I wrote here. We are trying to minimize, there shouldn't be any, we are trying to minimize Jj respect to Zj. And we explain why. Because no other, you can write them all, but they are all 0. Because eventually you want to take a derivative with respect to Zj, and they are not dependent on Zj. Okay, good. So in a sense, we are trying to minimize this quantity. Well, what is this quantity here? So we talk about this numerous times, but so I would like to work out this problem, and I did it actually in this note, but I'm going to go over that again. It's very important to be able to manipulate the norm and be able to write it as a dot product, as a vector transpose times the vector itself, right? So this is for the indices over in the cluster J, right? If it's hard, always visualize this one. This is cluster J. This is cluster J. We look at all the indices in the cluster J. Okay, good. So let's say that we have x1 all the way to a small n or in the cluster J, right? Okay, so we don't really care what points are in cluster J. I just want to show how to actually take a derivative with respect to that. Each point, you get this x1 minus, let's say for example, xi less than zj norm square. If you want to manipulate this, you get this, right? As long as you know how to do this one, this is good enough. Right, so you do it for all the points. And you don't need this summation sign, right? This is just an example. Assume that the first n data points are in the cluster J, right? So in general, otherwise you can keep it as it is, right? This is just to show you that what will happen if we want to, for example, say that Gj is equal to 1, 2, all the way to n, right? It's gonna be like that. It's very important to be able to manipulate this expression. I have it here. Let's go now here. So if you do this, you're gonna get, if you just expand this term here, what do you get if you expand this term? You're gonna get this one. So if you just multiply that, you get x1 transpose times x1 plus x1 transpose times negative zj plus negative zj transpose times x1 and then plus zj transpose times zj, right? Okay. If you do this one and simplify the expression, right, you will get something like that. Then you're gonna go ahead and differentiate this term respect to zj, because you want to minimize with respect to zj, and set it to 0. And that's what you get. This is what you get, right? If you simplify that further, this is what you get. The sum of xi, when the indices I are in the group J, equal to n zj, right? Therefore, the zj is equal to the average of the points in the cluster J, right? This is the cardinality, the notation for a cardinality, or a size of cluster J, right? Let's say, for example, cluster J is this. The cardinality is 5. There are 5 data points, right? So it's the same as the average you get, right? Instead of dividing by the total number of points, you divide it by the number of points for each cluster. It shouldn't be n. This should be I in Gj, right? Okay, great. So the best group representative is going to be the average of points per cluster. That's all you need to know, right? There are 2 things you need to know. 2 things. When the group representative is fixed, the best cluster assignment is cluster assignments that maps the data points to the nearest group representative. We talk about that. Then, if you fix the cluster assignment, then the best group representative is the average of data points per cluster. Okay, good. That's all we need to know, these 2 steps. Now we go to the k-means. This is general. Now we go to k-means. The k-means is the idea to iterate between these 2 steps. Fixing the group representative, finding the correct cluster assignment, then fixing the cluster assignment, and then updating the group representative. We do this one until we converge, until the J class, the value of J class, because we want to minimize J class, until the value of J class does not decrease anymore. This is one way as a stopping criterion. Another way that people use usually in literature is to define the iteration, number of iteration. They set it to be like 10,000 iteration, right? And then after that, so they choose, for example, 2 stopping criterion. They say the number of iteration and the error, right? The error between 2 previous steps of the J class. Is this one less than a threshold, or if the number of iteration actually has reached, right? So this is just the implementation tips. Now let's talk about the k-mean algorithm. You input list of n vectors, x1, x2, all the way to xn. And also the initial group representative. So initially, you don't know what is the best group representative. You have to choose randomly. You don't know which one is the best. You can choose one of the data points, or you can just randomly choose the group representative, right? Initially, you don't know the correct assignment. Initially, you don't know any group representative. You get the input vectors, and then you initially assign the group representative. Let's say randomly, or random number generated, right? K group representative. Then you repeat this until convergence, which we talk about the convergence, until the cost function doesn't decrease anymore, or the difference between the cost function and the current iteration and the next iteration is less than certain value, less than some epsilon, a small epsilon. Let's say 10 to negative 5, something like that. Okay, so you repeat until the convergence these two steps. One, you partition the data into K groups, right? The data is 1 to n, right? And assign xi each data point to the nearest group representative, right? So this is what you do in step 1. What do I mean? You have x1, x2, all the way to xn, and you have randomly generate the group representative, z1, z2, all the way to zk, right? You just go ahead and calculate the distance between these data points and the group representative, right? So, for example, you calculate the x1, the distance between x1 to z1, z2, and all the way to zk. You realize that the distance between x1 to z1 is the shortest. So you say that, you know what? I'm going to assign x1 to the cluster 1, or to the cluster corresponding to the group representative 1. Okay, very good. I do the same thing for x2. I do the same thing all the way for xn. So that's the first step, right? Okay, good. Then in the next step, you're going to go ahead and update the group representative. So what do you do in the first step? You're gonna choose the cluster assignment, right? So you have, let's say, 2 clusters for simplicity. You go ahead and this is the random cluster assignment that we have, group representative assignment we have, right? Z1 is the random. Based on this random assignment, you're gonna get some data points in each cluster. But then who said that this group representative that you chose for the first step was the best? You never know, right? Then you're gonna go ahead and calculate the mean or the average value of the points per cluster. You calculate the average of these points in the step 2, average of these points for cluster 1, and then you update the group representative. Let's say when you calculate this average, the group representative becomes here. Here, this is going to be the new group representative, Z1 new, right? And you do the same thing for the Z2, right? And then you realize that this is going to be this. Right? You keep doing this until the cost function doesn't decrease anymore, right? And until the group representative, or sometimes it's known as the centroid of the cluster, because we calculate the mean of the data points per cluster, the centroid or the mean of each cluster doesn't really change. But the best stopping criterion is just look at the cost function or the objective function, and then do something like this. For example, the absolute value of j class at iteration I minus absolute value of j class at iteration I plus 1 is less than, let's say, 10 to negative 5, some threshold, right? Then you know they should stop, because the objective function is not changing anymore. So 2 steps. Step 1, first of all, what do we get? We get a bunch of data points, which you go ahead and generate the group representative randomly, completely randomly. We don't know what's correct. We go ahead and calculate the distance between each data point and the corresponding K group representative for each data point. Okay, then we assign the data point to the nearest group representative. Then we're going to have a cluster, bunch of clusters, K clusters. Then in the next iteration, we have K clusters, right? For cluster 1, we have, let's say, 10 data points. We are going to go ahead and calculate the average of these 10 data points and calculate a new group representative, right? We do the same thing for other clusters as well. So now we have a new group representative, okay? We go ahead and calculate the distance all over again. The distance of all the points to the new group representative to see whether the clustering assignment is changing or not. Okay. Then after that, with the new cluster assignment, we go ahead and calculate the average of the data points in the new clusters to find a new group representative. We keep doing this until like some sort of convergence happens. Great. Okay, so this is the idea behind the k-means and most of the clustering algorithm. So that's it for this video. Thank you so much, guys, for listening. I will see you all in the next video.